So let's talk about nonlinear relationships. Regression models for nonlinear relationships. We've been talking about linear relationship, lines. Now all of a sudden this class has something for everybody. Right? Guys like a lady who has curves. Ladies like a guy who has class. Tonight we have a class about curves. No? No. No. No, it's never worked. That's my favorite thing about that joke. Polynomial regression models. So we've been dealing with variables that don't have an exponent. Y equals beta 0 plus beta 1x plus beta 2x2, etc. Now what if it's y equals beta 0 plus beta 1x squared? Next, use and evaluate log transformed models. So we might have the log of x or the log of y. And finally, describe the method to compare linear versus log transformed models. So what we're doing here is we're changing our variables to use higher order polynomials and log transformed variables. Why might we do that? We'll take a look. Ann Arbor is the data it uses. Polynomial regression models. A simple linear regression, and here's our formula, is easy to interpret. At least we've learned to do that. Sometimes a relationship cannot be represented by a straight line and must be captured by an appropriate curve. So remember this when we were first looking at our scatter plots and some of our data was U-shaped or parabola-shaped, and we said that this straight line is not the appropriate method. And I said, well, eventually we'll get into modeling this. Now it's that time. The assumptions of our model is that the beta terms are linear, not the x values. We assume linearity in our beta coefficients, not necessarily our underlying x values. So we can use this model to capture a lot of nonlinear data, like a quadratic model. And in this case, the book especially goes through a lot of economics variables. We are still an econ class, and the book relies heavily on economics terms here for examples and such, because this is one of the common places you find this used. You find log transformations and polynomial transformations in econometrics very often. For instance, an average cost curve tends to be U-shaped. A firm's average cost curve, you tend to realize economies of scale. If you build only one car, quantity, price, if you build only one car, it's very expensive to put one car together. But the second car you make is easier. And eventually they get easier and easier to make cars. So your average cost tends to drop, but only to a point. And eventually you start too many parts, you're tripping over each other, we're trying to make these cars, quality goes down, and we find that our average cost curve goes like this, as we have to build more and more and more. So where do firms like to produce? At a low cost point, of course. So, average cost curve tends to be U-shaped. Due to economies of scale, average cost initially falls, then rises after reaching a certain threshold. In this case, we would need to estimate this using a quadratic regression model. Our model is no longer our old y equals beta 0 plus beta 1x plus e. Now our model includes this squared term. Now keep in mind, this isn't a second variable. This is the same x. Y equals beta 0 plus this coefficient on x plus beta 2 on x squared. It's the same variable. It's just squared. So if we were looking at our data here, for different P's and Q's, price and quantity for making cars. I'll reorder these. For a certain quantity at a certain price. 1, it costs 100. 2, 98. 5 cars, 87. I don't know. So what we're saying here is price depends on quantity, right? Price equals beta 0 plus beta 1x plus beta 2x squared. And our x is quantity in this case. So for our first one, this is 1 and this is 1. For our second observation, this is 2 and this is 2. So we run our model on x and x squared. So we have to have an x squared term out here. 1, 4, 25, 36, right? So we're going to get 2 coefficients, 3 coefficients, an intercept, the coefficient on x, and the coefficient on x squared. This is how we'll build our data set to estimate something like average cost, something with a U shape. We use a quadratic regression model. The sign on your beta 2 determines whether we have this parabola, if your beta 2 is greater than 0, or this parabola, if you're less than 0. What if your beta 2 is exactly 0? Number 1, that's a bad variable, right? Because we don't need it, so that variable can be taken out. Number 2, it would just be a straight line across indicating a slope of 0. That variable is meaningless. So the sign indicates the direction of our U shape here. So here's our example. As we go forward, we gather 20 data points using a scatter plot. We notice a quadratic curve. So when we see this curve in our scatter plot, we need to be thinking quadratic. I'm going to need to square my variables. I'm going to need to square something to get this to fit. And here you see what I've drawn on the board. Average cost, output, and output squared. So we would run our model with this as our y, our dependent variable, and both of these as our independent variables. And then we would estimate our results. So we've done this before. Remember back when we looked at the scatter plots and we said, is a line really appropriate? We're like, well, not really. Remember when we compared Model 1 to Model 2 to Model 3 to look at which one might be appropriate? We're doing that again. Here's one without the squared term, and here's one that does have the squared term, with output and output squared. We compare our adjusted R squared, and we find a dramatic increase. Yes, adjusted R squared can be negative. Don't turn in that paper. That's 20 points off. Your final model has a negative R squared? What were you thinking? Oh, the things I see. See how dramatically well increased this model is by including that squared term? So our estimated equation is average cost equals 10.52 minus 0.3 times output plus 0.02 times output squared. Questions so far? We'll get practice on it. As a matter of fact, Gretel will square your terms for you just by, you click the variable and say add a squared term, and it'll just square them all and make a new variable. We'll show you how to do that on Wednesday. we interpret this, it's just too much fun to do. When the quadratic term is included, when you include output and output squared, for instance, you interpret the coefficient as the marginal effect of that variable on the independent variable. The coefficient is the marginal effect. What's the marginal effect? The effect of the next unit. So this is how you would find like a marginal cost or a marginal value. Really neat economics terms. The estimated quadratic model is here, and the marginal effect changes as x goes up. So in order to get that next change, in order to get this next, the change in average cost of the next unit, how would we find a change at a certain point? Come on, calculus friends. How do you calculate the change at a certain point on a curve?
The derivative.
Thank you. Oh, I was going to stand here till I got it. You take the derivative. And if we take the derivative of this function with respect to y, we can easily show that the marginal effect of x on y is b1 plus 2b2x. Remember, we bring our coefficient down. This drops off. This is a 1 coefficient. We drop down and reduce it as a short. Remember the power rule for our derivatives? How you can impress your friends who haven't taken calculus by doing the derivative in your head. So this becomes b plus 2 b2x. And then we can solve that for x and find a minimum or maximum. Remember this in calculus class, finding a min and max? So at this point we could tell our car company where you want to produce. We set our minimum and maximum to 0 and solve for x. Then we can find out what x we'll be solving. Good fun stuff. Going to be on a test? Nah, probably not this. You're probably not going to be finding min and max on test. But squared variables, probably going to be on a test somehow. When to use a squared variable, why would you use a squared variable, interpreting the output. This marginal and minimum is just too good to use. Can you do a third order? Can you do a cubed? Sure. 2 changes to slope. If, for instance, you had a variable that looked like that, in this case you would need a cubic model because it has 2 changes to slope. You can have a cubic model here. Very, very, very rare. Very rare. Really got to know what you're doing to make sure that that's the appropriate model. Very rare. An example of a cubic model, cubic regression, fine. Squared variables. Part 1 of nonlinear. Some of you look a little glazed over. What do we got? Too fast? Too useless? Too late at night? Too rainy and cold out? I don't know. Squared variables, I'm going to go over these more in depth on Wednesday, and we'll do examples in Gretel, and I'll show you how we do it. But I want to call back to when we looked at our scatter plots, because the big question is, where and why would we use a model like this? And it's when we see that our data is not linear. We might want to square it and add that squared term and use this model. We use them both the x and the squared x in the same model. And we interpret the coefficient v2 as the marginal change. So, in addition to squared terms, we can use log terms. We can use the logarithm of a term. And when I say log terms, I mean a natural log. I mean the natural log or logarithm base e. Logarithm base e. I mean a natural log. In Excel, it's ln number. It's log base e, where e is our natural log function, 2 point, etc., etc., etc. E is a number like pi, an irrational number. Our natural log, which describes things like radioactive decay, bacterial growth and load. We're using a natural log for a growth end. Another commonly used transformation to capture nonlinearities is the log, a transformation of your variable. So what we're talking about here are transformations. So we can start with our x and transform it to x squared. We can start with an x and transform it to the natural log of x. In the same way, and this is critical, we can start with an x and apply a multiplication or division to it. And in many cases it makes sense to do so. What if, for instance, one of your variables is U.S. federal budget? What's the U.S. federal budget every year? $5 trillion? So do you want your variable to look like that? And you want to do math on that? And then you come up with a coefficient that you have to multiply by that? Not really. What if we put this in terms of trillions? That's valid. Now you just have to remember you interpret it, your coefficient times 5 trillion. But you can do this. You can divide a number by something standard. You can put your terms in terms of trillions or billions or thousands. If you're comparing people's salaries, you might not want to have a list of salaries that looks like this, because this is hard to work on and hard to do math on. Instead, you might want to transform this variable by dividing by 1,000 and make this variable look more like that. That's legal. Instead of calling it salary, we just call it salary, comma, say it, in thousands. Yeah, that's legal. You can divide by thousands. That's fair. What if you're working with a batter's batting average? Batting averages are in the, like that, for a really terrible batter. For a really good batter, and anywhere in between. Well, percentages are weird to work with, so we might want to just go ahead and make it this, so that we transform our batting averages to, and just because they're nicer and easier to work with, that's a legal transformation. As long as you apply it to every variable, just makes your stuff easier to work with. These are linear transformations, right? All they're doing is shifting. They're a linear transformation. These are nonlinear transformations. Nonlinear transformations. Squaring and logging your variables. Very important. Linearity assumes that an increase in one unit of the explanatory variable has the same impact on the response variable, regardless of whether x is increasing. This may not be true, but if we want to predict something like how food changes to income, this is a useful model to use. There's a couple different ways to use logarithms. One is the log-log model. The log-log model, we're taking the log of our y, so we're trying to predict the log of our y equals beta 0 plus beta 1 times the log min x plus e. And again, we see logarithmic curves. Logarithmic as in exponential. Remember, if we have a linear growth pattern, like if I were to track my height over time from age 1 to 18, my growth pattern would look like this. Standard, I grow about a couple inches a year, whatever. A linear growth pattern. A logarithmic pattern is something else. A logarithmic pattern increases at an exponential or logarithmic rate. So we're not talking linear, we're talking logarithmic. Any of these are log curves. A log-log model, we're predicting a log with a log over here. Now, so we don't have to go all the way back to high school algebra and do logarithms. Let's simplify a little bit and change these logs in your head. When you see one of these, start thinking in terms of the change in. So when you see the ln, think, okay, we're predicting a change level in y based on a change level in x. How fast is y changing based on how fast is x changing? Let's think of it in those terms. Because what you're really looking for here is a slope. In this model, we would interpret the slope as the percent change in y given a 1% change in x. The percent change in y given the percent change in x. Income and years of education. So, if you want your income to go up by 1%, how many percent more education do you need? Or something. They're doing quantity demanded and price, and you're calculating elasticity, but think of it as a percent change in. That's the interpretation I want you to think of. The percent change in y given a certain percent change in x. The log-log model. We're predicting a change in based on a change in this. Okay? Again, we're going to do these. Prediction with these models is somewhat different. Prediction is somewhat different because we know a log-log model systematically underestimates. Mathematically, it underestimates. So we correct for that by using the standard error of the estimate. We force our estimate up by adding in the standard error squared over 2. We force our estimate up because we know a log model underestimates. Example, and we use an example with a standard error, 0.18 squared over 2, to force. That much is just our usual model, right? This much is just our usual estimate of what we do. Then we just add into the end the standard error of the regression, which we talked about in our diagnostic steps, squared divided by 2. It's just a fudge factor to push that estimate up. We'll practice it a little bit. So that's a log-log model, where we're estimating a change in based on a change in. The other way is a short logarithmic model, where we're still estimating y. We want the real level of y based on a change in x. how much more gas will I buy if my income changes by 10%? How much more bourbon will I buy if my income goes up by 50%? So we can estimate these types of change using a logarithmic model. In the last one, we had a log on y and a log on x. Here we just have a log on x. This is a lot more common. This is a relatively common model. A lot of times we'll want to log transform a variable to look at how changes in that variable really affect our model. Because remember, if we're looking at a graph and this is the actual, if we're looking at a graph of a number and this is the actual number, then this would be the log of that number. That's how our graphs would look. So sometimes if we have a variable that just goes off the charts nutty, and we see that our variable is nonlinear, we might want to linearize that variable. And we could do that by taking the log of it. We can linearize that variable by taking the logarithm of it. We do that in a logarithmic model, where instead of using x, we log x and use that instead. Very, very common. We interpret this as a percent change unit. Y retains the original, it is in units, and we interpret beta 1 as the approximate percentage change when x increases by 1%. We interpret it as a percent change unit. I've lost most of your eyes at this point, and your computers don't look fascinating. I'll go over these. I just want you to know they're out here. All right, let me give you the theory today, and we'll do them in Gretel, and I'll show you how it works, and we'll look at scatter plots. But I want to give you the vocabulary. I want you to know what I mean by transforming a variable, by squaring a variable, by logging a variable, and I just want you to know what that looks like. I want you to know that these transformations are out here. The exponential model is the opposite of the logarithmic model. This is where we log the y and leave the x alone. So you're seeing a pattern develop here, right? Log-log model, we log them both. Logarithmic model, we just log the x. Exponential model, we just log the y. You can try any of these out for your model. Here what we're doing is we're estimating the percent change in our y. So what might I need to do to make my income go up? What might changes in my income depend on? We're estimating changes. We interpret this log of y as the percent change when x increases by 1 unit. And this is our exponential model because it shows this sort of exponential growth curve, or exponential decline curve, as opposed to strictly a linear growth curve, an exponential increase. Finally get to use every data forecaster's favorite forecasting tool. The least reliable forecasting tool on the planet. If you have a certain amount of data, how do we forecast that data out? That'll be $200 an hour, please. Every data forecaster's favorite and least reliable forecasting tool. Exponential model, we log our y variable, our dependent variable. Again, we know that this underestimates. We know that this type of model, anytime there's a log in the y variable, we know that it systematically underestimates, so we add our fudge factor in. And we change our interpretation of it. We do an example. I like this slide. I like this slide because it covers each of these models, how we do the predicted variable, and how we interpret the slope coefficient. Although these models involve nonlinear functions, so our functions, our betas our x's are nonlinear, the beta slope parameters are still linear. We're not breaking that linearity assumption of the ordinary least squares model. So we can still use our same OLS model to estimate these. Even though our x's may not be linear, our beta slope coefficients will be linear. I like this slide. 27 in chapter 16. And then it goes through the data, plotting it. I don't like these. Testing your variables. We've seen this before. Looking at logs, looking at squaring, comparing your R-squareds. But I like that variable with the interpretations all on one page. Anybody have an obvious question about transforming your variables like this? Is anybody worried about diagnostic step number 5? Page back in your notes, what's diagnostic step number 5?
Are the variables correlated with each other?
Are variables correlated with each other? If I take a variable and square it, is this going to be correlated with this? Well, it's going to be a function of it. But when we say correlated, we're looking for a linear correlation, right? And this is now a quadratic correlation. So the variables are going to look more like these two. And are these two linearly correlated? Not really. So we don't have to worry about whether or not we don't have to worry about multicollinearity as much. Same with these two here. Now if we do a transformation like this, and if I include both of them, like we do here, here we include both terms in our model, right? Down here, I don't want to include both terms in my model. I don't want to do y equals beta 0 plus beta 1 salary plus beta 2 salary in thousands. In this case, these two things will be very correlated. Matter of fact, the lines will look like that. And they'll be perfectly correlated. What will happen is it will flip the coefficient on one of them, and your R squared will jump to 99%. It will turn the sign of the coefficient of one of these two negative, your R squared will jump to 99. Because these two will be perfectly linear. It's perfectly okay, though, to do y equals beta 0, beta 1 salary, beta 2 salary squared. This is okay. Questions on nonlinear models? On Wednesday, I'll show you how Gretel does these automatically.